I'm Masaki Naito from Nihon University, Chiba, Japan. And actually, it's cold day in Chiba. Its temperature is about 10 degrees Celsius in Tokyo, and it's 5:30, around 5:30 in Japan. So we'll talk about an example of how Capella can be used for CubeSat development. Um, so next slide. So today's content is like this. First, we will introduce about ourselves, and next, we will talk why we adapted Capella. We will talk about space systems and CubeSats, and also what we hope to achieve with Capella. And after that, we will show you our Capella model and our satellite and the software designing using Capella. And after that, we will have conclusion. So first about myself, my name is Masaki Naito, and I am a fourth year in Nihon University. We are developing 6-year size satellite PRELUDE. This will be actually main topic of today, and I am sub manager and system integrator and also onboard software developer. And my research topic is CubeSat software modeling and optimization by using MBSE, of course, including Capella. And actually, this session starts at 5:30 in Japan, but I thought that this session starts at 4:30 for 2 months. So I misunderstand about third time, but yeah, I'm here and I'm really happy to be here and make this presentation.
Thank you. My name is Masahiko Yamazaki. I'm an associate professor in the Department of Aerospace Engineering, Nihon University, and the vice chairman of the University Space Engineering Consortium. And my research topic focus on the satellite design, development, and operation and education. So these images are such kind of examples. The one is the educational satellite. The one is satellite with the deployable structures, and the one is electrical field observation CubeSat, and upper one is the capacity building program tools. We make educational kit and the educational training textbook for the students and the engineers and the researchers. They want to understand the CubeSat. Next slide, we will give you the brief overview of our laboratory research and the project. Our laboratory basically, and these days, tackle the three topics. The one is the PRELUDE satellite project. It is a miniature size satellite project, and we will launch next physical year. This satellite focus on the observation of earthquake precursor. And then this project that integrates science side and engineering side through industry, academia, and government collaboration. And today's presentation topic focus on this satellite design and development and operation. The second topic is that second of our research and project is the Neptune satellite project. This is also the small miniature size satellite project, nanosatellite for early tsunami prediction. The third project is the heptasatellite training project. This is a capacity building program and a capacity building project through CubeSat hands-on practice. So our laboratory basically focus on the satellite space-related design, development, and operation and education, and focus on the modeling of satellite systems and the satellite observation data and solving social problems. So from here, we will give you the short summary of why we adapt the Capella to our satellite system. Before I explain the details, I will give you the brief introduction about the space systems and the CubeSat. This slide shows what are space systems and what is a space system and what is systems. From our understanding, a system consists of various elements such as hardware and software and people and data and service which work together appropriately to achieve a goal. this left figure consists of the operate ground station operators and ground stations and the satellite itself, and then there is the ground sensors. Each sensor and each element has interfaces between each element. Interface 1, 2, 3, 4, and there is the component 1, 3, 3, 1, 2, 3, 4, and the satellite itself also has a several component element like light figure. There is a component A, B, C, D, and that become construct a subsystem A, and there is a subsystem B, and subsystem A and the subsystem B connected by some interfaces. And there is a requirements about the component, about the interfaces. So it is very important to clarify the requirement to develop such kind of system. So developing such kind of space system means clarifying the boundary of the system and the designing and operational and functional and the physical design that is consistent with the requirement and the constraint of the entire life cycle. This is very important, and this is our understanding. And then evaluate from the variety of perspectives, both numerically and experimentally. And this figure shows the general and basic satellite concept. It consists of the basic element like thermal control system, and attitude control system, and orbit control system, electrical power control system, and communication system, command and data handling system, and structure and mechanical system. Based on these elements, basic elements, or supported by these basic elements, payload system is there. So payload do not operate by themselves, but rather execute their roles in combination with other onboard hardware and software and interfaces. So we think it is very important to deeply understand systems for developing system. Next slide. From the next slide, I will give you the short introduction about the CubeSats. The definition of the satellite classes are slightly different from the country to country. This is one of the example of the definition of the satellite classes. It started from the pico satellite and to the small and medium satellite. This presentation focuses on the pico satellite and nanosatellite, and basically we call the CubeSat. And large satellites are multiple purpose and used on highly accurate missions. And the pico, nano, micro satellite may perform similar mission as the large satellite by forming a constellation. It means using the multiple satellite. The CubeSat come in several sizes, and which are based on the standard CubeSat unit called 1U. The 1U is a 10 centimeter and a 10 centimeter and about 10 centimeter. And CubeSat has several standards and regulations. It's for example, size regulations and weight regulation and shape regulations. The specific standard regulation for CubeSat help reduce cost. And 1U CubeSat is a 10 centimeter cube with a mass of approximately 1 to 1.33 kilograms. And this slide shows the left picture shows an example of University Space Engineering Consortium in Japan, satellites from 2003 to 2019 for R&D and commercial. Already better than 50 satellites already launched. Nanosatellites that can be developed at low cost and in a short period of time, and they are being used, such as being utilization in education and business and science, and not only replacing the conventional technology or conventional large satellite, but also complementary to them.
Thank you, Professor Yamazaki, and I will talk about what we hope to achieve with Capella. So in the real space project like our CubeSat development, it is sometimes hard to gain or understand knowledge or experience of the whole development process or every subsystems because the roles are divided among team members. So even if we belong to a specific team and learn part of it, there are few opportunities to learn the entire satellite system. So you may, if you're in charge of structure subsystem, you can understand and you can develop or design structure, but it is not easy to understand sensor subsystem or to discuss about it. So everyone should know and understand how the system is built from components, understanding the relationship between the entire system and its elements. So at, in that sense, MBSE provides a visual understandings of other subsystems or whole satellite system and the overall satellite system, leading to a design that optimizes the entire satellite. Not only that, we have other 3 points that is we hope to achieve with Capella or MBSE tool. So first, not necessarily created by professionals, which means we are students. And these days, many new companies are starting to develop CubeSats. So design and verification omissions are likely to occur. So many university students or those beginners are not familiar with satellite design and verification. But verification omissions can lead to the loss of the satellite. So drawing and visualizing the model diagram makes it easier to notice omissions that will make our mission better, and we can get more data or what we wanted to do. And second, in a university institution, knowledge and technology losses occur due to member turnover. So high turnover rate, about 1/3 members graduate every year. And actually our laboratory has only around 12 members this year, but 3 of them will graduate this year. So by leaving information on the model diagram, it is easier for new members to understand the system. And not only new members, but also those members like now we can understand and discuss by viewing those models. And third, it is necessary to develop the system under severe constraints of time, budget, and human resources. CubeSat is small, so we don't have to consume a lot of budget, but that means we have to make it with a little amount of budget. So we want to optimize satellite system design and development process to accomplish our mission with limited resources. So next, we will talk about our CubeSat Prelude. In 2004, the small satellite Demeter was developed by CNES, which is French Institute, to investigate earthquake precursor in the ionosphere. And Demeter satellite is this figure 1, and its mass of about 130 kilograms. And our satellite is actually 8 kilograms. So our satellite is really small compared to this satellite. And according to this research, about a 1.7 kilohertz electric wave intensity decrease about 4 hours before earthquakes. And it is statistically significant. So which means if we have more data, we can predict earthquake before 4 hours before the actual earthquake. But as of now, the mechanism behind these fluctuations remains unknown. So we don't have enough data to analyze or to short. So there is a shortage of major earthquake cases with high quality data. So we need more data to predict earthquake. So to increase the number of ionospheric observation data and clarify the mechanism of the phenomena, we are developing the PRELUDE satellite. as I talked in the last slide, PRELUDE is quite small, so and also development cost is not large, so we can develop these satellite many satellites. So which means constellations. By using constellations, we can get more data, and we will launch satellite like this launch state. And after launch, we will deploy solar panel and also 1.5 meter extension boom to acquire data. Here, electric field and plasma hybrid sensor probe is located in the top of extension boom. And this will be launched by Japanese Space Agency JAXA Epsilon S rocket in next year. And our orbit is sun-synchronous orbit, so it will turn around the Earth. So we have three main missions in PRELUDE. First, detection and statistical evaluation of earthquake precursors. And second, development of a 3U size payload for electric field and plasma hybrid observation. So not only observe the earthquake, but also we are aiming to develop this kind of kit or hybrid sensor unit for other researchers. So it's only 3U size. 3U size means about 10 centimeter, 10 centimeter, 30 centimeter. So, and it also has simple interface, and it can also be equipped on other satellites. And the third mission is development of CubeSat platform for electromagnetic observation, reducing electromagnetic noise and constellation through international collaboration. And this is mission sequence and overview of our satellite. Once satellite is launched, and after few seconds, solar panel will deploy in order to get power. And after that, will extension boom unit for electric field and plasma observation. And ionospheric observation, by observing lightning and artificial VLF waves when the satellite passes over the epicenter, the ionospheric changing preceding earthquake can be detected. So that's a brief introduction about our CubeSat PRELUDE. And next, I will talk about software design and satellite system design by using Capella. Maybe as most of participants already know, that analysis in Capella is like this. First, we will start from operational analysis, and after that, we will move on to system analysis, which can find functional and non-functional needs. And these two layers will be black box approach, and the next two layers, logical architecture and physical architecture, will be white box approach. And in logical architecture, we can find how the system will work to fulfill expectations that we find in upper two layers. And physical architecture, how the system will be developed and built. And in our case, we actually started using Capella last year. And at that time, the satellite system was already designed before we started using Capella. So actually, we use Capella for verification or optimization for our satellite system. And our satellite main developer is Nihon University, so we are main developer, and we are responsible for all system design, development, and operation from overall satellite design to operation. So we mainly use the logical layer and physical layer for verification of the satellite system design and optimization. But as of now, we are still making models in physical layer, so we're in logical layer now. And our objective of operational layer was identifying stakeholders and clarifying the boundaries of the system. And in system layer, it will be expression of functions required for the entire satellite depending on the mission. And in logical layer, expression of function required for subsystems, and in physical layer, expression of functions required for components. So let's see our operational layer diagram. This is operational capabilities diagram. And here, as you can see, main developer and main operator, Nihon University, and mission control center is here. And we want to get data from space or ionosphere. So space is here as entities. And also there are several other entities like rocket launcher or ground station. But we could find stakeholders and also operational capabilities in this diagram. And after making this diagram, we moved to operational architecture blank diagram. Here, there are same entities and main developer here, and space here, and mission control center here. But our main target is to get data from space through ground segment and our mission control center. And after that, we will analyze the data. So when we develop satellite, we focus on this part, satellite operator and ground station and space. So in system layer diagram, we focused on these two, this part, and we made this diagram. So here, space and satellite and ground station operator are there, and it is expression of functions required for the entire satellite. So we don't mention about our subsystems, but here several functions required for satellite is appearing. And in operational layer, we only talked about operations activities, but in this system layer, we can find that if satellite health or like that, not only the functions required for the mission, but also the function to maintain the satellite are necessary. So if we focus on this keep satellite health in next logical layer and logical function breakdown diagram, here requirement from the system layer keep satellite health is here. And in logical layer, we will break down those requirements in subsystem levels. So keep satellite health is achieved by monitor satellite health every second. And it also required the new housekeeping data. Housekeeping data means satellite status data. So for example, satellite temperature or current data or like that. And it can also divide it as attitude data or communication data or mission data. So we could break down from requirement from the system layer and a seamless approach to logical layers. So by breaking down the necessary elements for the entire satellite, it is possible to identify the necessary functions of the software without omissions, leading to improved reliability. So this is logical architecture blank diagram. You can look at the model of the entire system, or you can focus on individual parts. But here's power supply system, and here's data handling and communication, ground segment, attitude control, and mission system. But the important point, I think, is the function found in logical function breakdown diagram is here. So the function from the system layer and breakdown element is here, allocated as a part of attitude control subsystem. So, but our main target, or we are aiming to improve reliability or traceability for data handling software. And we use Capella primarily for software design optimization. And we consider the following three keywords to be important as indicators of optimization. So first keyword is reliability. Once the satellite is deployed in orbit, only software can control its behavior. And we can't touch satellite or we can't talk to satellite directly. So therefore, reliability is needed in satellite software. But not only reliability, flexibility is also important because sometimes unpredictable events occurs in orbit, and some things you just don't know until you launch them. So satellite must have flexibility to deal with those unpredictable or undesirable events. And third, reusability is also important because even other satellite or different satellites share the same basic functions. So I think every satellite has a function to keep health. So if we, if those common parts can be used, development time can be shortened, and also reliability will increase. So we think reusability is also important. So in order to achieve those keywords, layered architecture, we have layered architecture in software, and I think this is quite common approach in software development. But upper layers are abstracted so that they don't need to change even if hardware changes. So first, or most abstracted layers is application layer, and driver layer will be like a function to control components. So it is more detailed layer. And hardware abstraction layer abstract hardware dependencies. So, but I think application layer is a layer for what the user or what subsystem wants to do or has to accomplish. And driver layer is a layer for how to do it. So driver layer will have a function of communication between other computer or like that. But in application layer, the function will be monitor satellite health or like uh, easy to understand even for humans. And logical analysis and the physical analysis, we have compatible with application layers and driver layer. So logical layer can identify requirements for subsystem, and application layer in software will also have those functions. And in physical layer, it's also the same concept, but driver layer will have a function to drive components. So by using those uh, architecture, there is no need to change the upper layers, even if the lower layer change, thereby improving reusability. So we can improve reusability with software, and also we can improve reliability. So this is a logical architecture blank diagram again, but uh, this time we only focus on functions related to monitor satellite health, just as example. And logical architecture blank diagram, focusing only the equation of HK data. And a program with the same function was created based on that diagram. So as we found in logical architecture blank whole satellite system diagram, uh, for example, in ADCS subsystem, which means attitude control subsystem, there are get ADCS HK data. And in satellite software, there are also same function name here. So by using this diagram, you can understand software, not viewing actual code, but you can understand by viewing those models. So the same functions as in the model are implemented in the software so that we can understand the software visually. And also, we talked about reusability and reliability in a previous slide, but this approach will enable us to improve flexibility. And we have single command and macro command in satellite. And single command means command to control satellite movement or behavior. And macro command is a series of operations can be called up from a single command. So macro command contains several single command, and those several single command will achieve one objective. And in Capella, I think their functional chain, function A and function B and function C and function D will achieve one objective this by using this chain. So I think Capella and functional chain is useful when designing macro commands and also reordering single commands and considering those in what is optimal in orbit. So that's all about our satellite model. And as a conclusion, what we have achieved with Capella. And by looking at the model and discussing it, we were able to clarify the requirements for the system. So we could logically derive criteria for success failure of the system, which is called success criteria. And also by deriving the software module partitioning from Capella, the logic of the software design became clear. So the team was able to share the concept of the software design, and also we could discuss, and also reliability, reusability, and flexibility of the software were improved. And in the future, so this is just a concept for now, but we would like to apply the functional chain concept to software or macro command so that we can increase flexibility. And as future plans, now it is mainly used for software design and success criteria design. But in the future, I would like to use it for system design. So, for example, whole system design, which means our next satellite. And also, I would like to actively utilize Team for Capella, where everyone does the modeling instead of just one person. So now we are mainly using Capella, so software design. So only me is using Capella. But by using Team for Capella, we can share the same audio and we can edit at the same time. So we'd like to make it a common language within the laboratory so that all members can use it. So that's all for our presentation. Thanks for listening.
Okay, thanks for this presentation. Maybe a question from my side, waiting for those from the audience. So I just wondering if you have connection with other entities doing the same kind of CubeSat development, and if there's an interest in exchanging models.
So I think we don't have those connections or yet, but we're interested in those other models.
Thanks for that. Any intention to model variations between the different satellites with the product life management?
We have a plan. So we are thinking about the connection between the another organizations by using the Capella and this kind of models. And we also considering that to develop the lots of satellites, same type satellites to observe the ionospheres. So we need to manage products lines using these models and future models.
Okay, thank you. Next one. Are you using any tools to convert Capella model to another software development suite to generate code, or are you generating code by hand?
Actually, we generated or we made code by our hand, but if we want to generate code by automatically by using some tool. Yeah.
Okay, thanks. So is the decision to introduce reusability induced by the use of a model?
Okay, so I think reusability itself is well achieved with those software architecture, but I think those architecture are compatible with Capella. So those compatible, we will increase reliability, and at the same time, layered architecture will increase reusability. So by using those architecture and Capella, we can improve those 2 points.
Okay, thanks for that. Was there one modeler in the team, or different people were adding their parts?
So for only one moderator now, but we are planning to use it in whole laboratory. So some members will make model. So we will use it as different people will add in those parts.
We are 6 undergraduate students and 5
Graduates.
graduates. 6 graduated students. So
Okay.
now modular is 1.
So, did people who looked to your model understood it quickly, or they were not responsive to jump into your model?
I think model. It depends on model, but in most model, understanding model is quite easy because we can visually understand. But if we talk about software and relationship between software and model, it might be not so easy so far to understand completely about software. So I think by using those auto generation or by thinking those idea more, I think we can achieve more good situation.
Okay, and is your MBSE solution part of a larger solution? Is there any requirement tool, IVV, simulation, or hardware design tool also linked with this architectural approach?
Yes, this presentation outcome is one of the solution of our systems engineering activities. The design and development and operation of the satellite, there is several types of system engineering problems. For example, electrical power supply management, design and development, and the simulation and evaluations, and attitude control, design and development, and simulation and evaluation, and the structural design, like that. So each design, development, and simulation and evaluation will connect this model in the future. Not yet. We are still considering, still working the such kind of models, and we want to make the truth of source. So we want to make. We think that such kind of satellite system model become the truth of source. This is my opinion.